Okay, we've heated up the air to 360 or 363 Kelvin. We have 500 milliliters of air in the bottle. That took about 25 joules of heat energy. And now we're going to continue to heat the air, and now water is going to come out the top, okay, because it can't go any higher. It's going to come out the top, and we're going to start displacing a significant amount of air, not just the 4 milliliters we hypothesized before, but a more significant amount. Matter of fact, we want to see what has to, how much temperature change we have to have in order to displace 100 milliliters of water, which incidentally is impossible for that bottle. It's only got a capacity of 591 milliliters. So we just assume a slightly larger bottle. Okay, so we're at 360, 120 kilopascals, 500 milliliters, and we want to expand at constant pressure to 600 milliliters. What do we have to do? Well, we can use PV equals nRT as we did before, but this time I'm just going to reason this out intuitively. We're safe to say, well, we have 6/5, we're going to have 6/5 of the volume. 600 over 500, 6/5 of the volume. V over T is constant this time because the pressure is, well, the volume's, yeah. We have PV equals nRT. Pressure is going to remain constant because we're already at the top. We have a 2-meter column, and that's all we're going to have. Water is going to come out. So pressure is going to remain constant, and N and R remain constant. So V over T is constant. And that means that 6/5 of the volume implies 6/5 of the temperature, so that the final temperature is going to be 6/5 of 360 or 432 Kelvin. Now you can analyze this using more symbols, but eventually you get the intuitive idea that the warmer it gets, if the pressure is going to stay the same, the volume has to expand in the same proportion as the temperature. Now, question, what's the change in potential energy now? We've expanded this thing by 100 milliliters. Well, if the air in the bottle expands by 100 milliliters, it can only do that if 100 milliliters of water has left, because the volume of the bottle isn't changing. So we know that there's 100 milliliters of water being raised to 2 meters. What's the change in potential energy? Well, that's a very straightforward calculation. You should be able to do that easily, but let's just go ahead. The weight of the water is about 1 Newton. That's 100 milliliters. That's a tenth of a liter. A liter is a kilogram, so a tenth of a kilogram multiplied by 9.8 meters per second squared gives you 0.98 newtons. So we're approximating that as 1 Newton. So the potential energy change is 1 Newton times the 2-meter upward displacement, or 2 joules. Now, how much heat is required to do this? We saw that we needed, first place, 25 joules of heat to raise the pressure enough to get up to the 2-meter column. And then what? Then we have to expand this thing, and it turns out we're expanding it against atmospheric pressure. It takes even more. We have more of a temperature change, and we now at constant pressure have a constant pressure CP of 7/2 R for this phase. So we're going to get considerably more than the 25 joules. I'm thinking we'll get around 60 to 70 joules. Haven't worked it out, but by proportion, maybe even a little more than 70 joules of heat required to accomplish this. What's the efficiency of that process? We got 2 joules of energy for probably about 70 joules of heat. Now that comes out around a 3% efficiency. Now that might be regarded as a terrible efficiency, but that's the best efficiency you can get with these temperatures, as we'll see later. And in addition, the heat energy, if we have a good geothermal source, for example, is really cheap. So 3% of something that's really cheap might be better than 20% of our gasoline, which is cheaper these days than it was a few months ago. But that's not going to last, okay? So we make those comparisons based on what's available, what it costs. Working at 3% as opposed to an internal combustion working at 15 or 20%, doesn't seem like a good deal. And of course, we can't run a car on a heat engine like this. It would be kind of slow. But as far as generating power, maybe that 3% is good enough to beat other sources. In some circumstances, it certainly is. In other circumstances, it certainly is not.